our last example in Nyquist stability criterion. And remember, we are doing always the same thing. I start with an original contour in the S-plane. And this contour is called the Nyquist path, and it has clockwise rotation or clockwise direction. So I will mark the poles and zeros of the system first there. Zeros do not matter for us, so the contour can pass through zeros because we are checking the encirclements of the point -1/k. Zeros do not matter for us, but the poles will matter. And the poles of that thing, that transfer function, there are double poles at the origin, and there is a pole at 2. Okay? And there is a 0 at -1, but it's not important in the Nyquist stability criterion because we are checking the encirclements of the point -1/k. If we were checking the encirclements of the 0 point or the origin, then it would have mattered. Then in that case, I wouldn't pass that contour from a 0 of the system. But currently, it is not. It doesn't matter. So that actually means that I only have to avoid the poles of the system on my Nyquist path. And when I draw the Nyquist path, it's going to be a semicircle with infinite radius. And I see that if the contour should pass from the imaginary axis, but as you see, if I complete the origin, then the contour is going to pass through one of the poles, or two of the poles there. I really do not want that because I'm going to do a similar thing that I did in the last lecture, and I'm going to go around them, okay? And then I'm going to actually give some names to different points here, A, B, C, and D here, and then I will transform this contour from this N over D. N over D is S plus 1 divided by S squared, S minus 2. Okay? So the first thing that I'm going to do is that I will parameterize the part from A to B. So when I parameterize the part A to B, I'm going to write S equals to epsilon e to the j theta. And here epsilon should go to 0. Okay? This is going to be the part where the Nyquist plot is going to be infinite. It's going to blow up because this distance is going to go to 0 as epsilon go to 0. So this part from A to B of the Nyquist plot is always going to be at infinity. And when I look at this part from C to D, I see that S is now at infinity. If S is at infinity, this transfer function is going to be equal to 0. And that actually means that this part of the Nyquist plot is going to be at 0. This part of the Nyquist plot is going to be at infinity. And this part is going to be the frequency response of the system. Frequency response of the open loop system here. Okay? And this part actually is going to connect to the topic of Bode plot at the end, because this part is nothing but the frequency response of the open loop system. Here we are always doing the same thing in this course. We are given the open loop system. We are given the Nyquist plot of the open loop system, and based on the open loop Nyquist plot, we are given the Nyquist plot of this thing. Given the Nyquist plot of this thing, or we are drawing it, after we draw this, we look at the closed loop stability. In the coming topic of the course, we are given the Bode plot of this thing. That is, again, the open loop system. Its Bode plot is going to be given to us, and we will design our controller, closed loop controller, using that Bode plot. In root locus, we did the same thing. We are given the open loop transfer function, again, the same thing, and we found closed loop pole trajectories. Okay? Well, doing the same thing over and over. In state space representations, the last topic of this course, we will be given the state space representation of the open loop system. Then we will design a feedback rule, and we will try to optimize the closed loop state space representation. So everything over and over, but with different representations of the systems. Okay? Each part of control theory is based on some representation of the system, and using different representations, you can try to achieve similar aims. Epsilon goes to 0, and theta changes from where to where? From A to B. I have to put directions here always. Okay? So this is a clockwise contour. That is why I'm always checking. After drawing the Nyquist plot, I need to count the clockwise encirclements of -1/k. So here theta is going to change from where to where? Sorry? Yes. So we are going to increase from 0 to 90 degrees. Okay? And now I'm ready to substitute this representation into my n over d. Remember that when we transform this representation by n over d, then we are obtaining some part of the Nyquist plot. So here, if I substitute this, n over d is going to be epsilon e to the j theta plus 1. I'm just substituting s equals to epsilon e to the j theta. Then this is going to be s squared. It is epsilon squared e to the j2 theta. And I have epsilon e to the j theta minus 2. Okay? When epsilon goes to 0, these numbers here, I am summing 1 with something very, very small. So this is going to be negligible, and this is going to be negligible. Okay? And when I write the remaining quantities, I get 1 over epsilon squared e to the j2 theta, and I have minus 2 here. So now I'm going to continue trying to process this ratio, but I'm going to process it wrong. Okay? So if I ask you this question in one of the exams, then half of the students would do the mistake that I'm going to make. Okay? So here there will be a mistake in the things that I'm going to write. So try to find what is going wrong here. 1 over minus 2 epsilon squared e to the minus j2 theta, and I will write this as r e to the j phi. Okay? And then r is equal to minus 1 over 2 epsilon squared. Epsilon goes to 0. This thing would go to infinity. And I have phi is equal to minus 2 theta. And minus 2 theta starts from 0, 180 degrees, goes to there, and it needs to minus, and it should decrease. Okay? What is wrong? Something is wrong there. This is not going to be the Nyquist plot.
Minus 2 degree.
Yes, the problem is at minus 2. What happens there? What is the problem there?
Is that associated with minus 2 phases?
Yes. Yes, that minus 1 there has a phase itself. Okay? It's 180 degree phase, and I'm neglecting it completely in this type of analysis. So it doesn't make sense. If you continue in this manner, then things will not match in your Nyquist plot, and something is going to go wrong at the end. You will be confused, and then it's not going to be good at the end. So here, this minus 1 here, it is not a positive real number. It has a phase itself. It's 180 degree phase. Okay, so that actually means that I shouldn't continue in this manner. But instead I should do something like this. So I'm erasing this part. So I have to do the following. I'm going to take this minus 1. I will write it e to the j 180 degrees. Okay? It is something like this, and I can write this as 1 over 2 epsilon squared e to the j 180 plus 2 theta. Okay? So now I can write this thing as this is equal to r times e to the j phi here. And I can say that r is equal to 1 over 2 epsilon squared. Since epsilon goes to 0, this is going to go to infinity. And I can write this as 1 over 2 epsilon squared e to the minus j 180 plus 2 theta. That means that this phi here is minus 180 plus 2 theta here. Okay, there is a minus sign here. So you see here in these angles now there is the 180 that we have forgotten in the last analysis, the wrong analysis. Okay, so now I can write what this theta, what this phi, how it would change. It is going to start from theta is equal to 0, meaning that it's going to start from minus 180 degrees. Okay. And when theta is 90, this is going to be 360 minus 360. And because of this minus sign, instead of increasing, this is going to be decreasing. Okay? This is the correct analysis that you can do, and you will see that compared to the earlier wrong analysis, these angles are shifted by 180 degrees at the end. Okay, that is because of the minus sign that I have forgotten in the earlier analysis. So now here I see that at radius infinity, I need to turn 180 degrees. If this was cube instead of square, if this was cube, how many degrees should I turn at infinity in that case? Yes? 270 degrees. Okay, so the amount of the number of degrees that I turn is determined by 90 times this power here of s. If this is 3, I'm going to turn 270 degrees. If this was 4, I need to turn 360 degrees, etc. at infinity. So now let me go to the other part. From part B to C, I see that S is equal to j omega, and this is going to be nothing but when I substitute S equals to j omega, this is going to be the frequency response of the open loop system. And when I try to draw the part from B to C, what I'm drawing is that I'm drawing the frequency response of the open loop system into my N over D plane. Okay, and that part. This is the part actually given by MATLAB, for example. If you try to draw a Nyquist plot in MATLAB, you're only going to get the part from B to C, and from this point, you won't really get the parts at infinity. Obviously, how can you get it? So in MATLAB, you will only get the part from B to C when you try to draw a Nyquist plot, and instead of drawing a Nyquist plot from B to C, we can try to draw the magnitude and phase of that quantity separately. And that becomes a Bode plot. Okay? So instead of drawing a Nyquist plot, we can draw the magnitude and phase of the same thing on separate plot, and that would give us the Bode plot, which is going to be the next topic that we will start today. So here let me do that substitution. S equals to j omega. N over D is equal to, I'm substituting j omega instead of S, so I have j omega plus 1 and minus omega squared, I have minus 2 plus j omega. And here I can write, instead of j omega plus 1, I can write 1 plus j omega. Okay? It is this substitution. Now I will try to make the denominator real and positive. So I will take the minus sign above, it is going to be 1 plus j omega, and I will multiply both numerator and denominator by the complex conjugate of this complex number in the denominator. Okay? It is going to give me minus 2 minus j omega, okay, divided by, I have omega squared, and I have here 4 plus omega squared. Now the denominator is always real and positive. Here, omega is going to change from B to C. How is the change of omega? Omega is going to change from where to where? It is going to start from epsilon, it's going to end at infinity, okay? And it's going to increase like this. So here the important point is that omega never becomes 0 here on this part. If omega can become 0, that thing would be infinite, and I wouldn't know its phase. Things going to infinity does not really matter for us in drawing the Nyquist plot. What matters for us is that I need to know the angle at which it goes to infinity. Okay? Because I'm counting the number of encirclements, I'm interested in the angle of the points there. Okay? If some quantity goes to infinity, I need to make sure that I know its angle, how it goes to infinity. Okay? So here I'm going to continue processing this thing. So let me cancel these minus signs. So I have 2 plus j omega here. And I can here look at the real part is going to be 2 minus omega squared plus j 3 omega divided by omega squared 4 plus omega squared. Okay? Now I can clearly see the real part and the imaginary part of this quantity. The real part is 2 minus omega squared divided by this denominator. Imaginary part is 3 omega divided by this denominator. So now I'm ready to make a sign table for the real part and the imaginary part of n over d. So I have real of n over d imaginary part of n over d. I need to determine some critical frequencies where we have a sign change in the real part or the imaginary part. Where does the imaginary part change sign in this interval from B to C? It doesn't change sign, but this becomes 0 at omega is equal to 0. Omega is not 0 in that interval. It starts from epsilon and it goes to infinity. Okay? That means that that critical frequency doesn't exist in this interval. I say that omega is going to be equal to square root 2 in that interval. Omega is equal... Why do I not take minus square root 2? Because from B to C, I'm only considering positive frequencies. Okay? So that is why I should not really consider. So here we see that all of the frequencies are positive ones, and the real part becomes 0 here. And if I look at the signs here, if omega is smaller than square root 2, the real part is going to be positive, imaginary part is going to be negative, so real part is going to be negative here. And imaginary part is always positive in that interval. Now I will investigate what is going to happen when omega goes to 0, and I will investigate what happens when omega goes to infinity. Okay? When omega goes to 0, the smallest power of omega is going to be valid for both the real part and the imaginary part. What is the smallest power of omega in the real part, in the numerator? It is omega to the 0. So the real part, in the real part, the smallest power of omega term is going to be just 2 divided by smallest power of omega in the denominator. It is 4 omega squared, and I will let omega go to 0. We see that it goes to infinity on this part. Real part goes to infinity. What about the imaginary part? The smallest power of omega there is 3 omega divided by 4 omega squared. What is that limit as omega goes to 0? It's going to be infinity as well. And when I look at the behavior as omega goes to infinity, then the largest powers of omega will be valid. The largest power of omega in the numerator for the real part is minus omega squared. The largest power of omega in the denominator is omega to the power 4. That means that here, this one is going to go to 0, this one is going to go to 0. Okay? So here, then I'm going to evaluate n over d at the critical frequencies. Then it's going to be n j square root 2 divided by dj square root 2. It is going to, I can evaluate it anywhere here. And I'm going to evaluate it here. I have j, 3 square root 2 here, divided by, when I substitute omega is equal to square root 2 here, this is 2, and this is 6. Okay? So then I'm going to cancel 2 here. It's going to be j square root 2 over 4. Okay. And as the final thing in this analysis, I'm going to let omega go to 0, omega go to infinity. I will look at the angle of n over d. What do you think this angle is? If omega goes to infinity, then s is going to go to infinity here. If I let s go to infinity, how can I approximate this transfer function? It is going to be 1 over s cubed. Do you think it's correct? As s goes to infinity, this is going to be approximately s divided by s cubed. Then that is going to give me 1 over s squared. I have s is equal to j omega, and each of the s's here will bring me minus 90 degrees phase. Okay? That means that this angle is going to be what? Yes? Don't be shy. You can shout.
Minus 100.
Yes, minus 180 degrees. Okay? So as I told you, this angle, If I was drawing the Bode plot of the same thing, then when I look at the Bode plot, the phase plot, that plot would end at minus 180 degrees. Okay? So here, this angle is only determined by the relative degree of the transfer function. How many poles there are more than the zeros? Okay? There are 2 more poles than zeros of that transfer function, and this angle is going to be minus 180 there. And finally, the easiest part of the analysis is going to be the part from C to D. From C to D, S is equal to R e to the j theta, and R goes to infinity, and theta starts from 90 degrees, and it decreases to 0. Okay? I have drawn this part of the Nyquist plot around 0, tiny circles around 0, and this part is not really important for us, because we are not checking the encirclements of the origin. And that actually means that in this case S effectively goes to infinity. When S goes to infinity, what is this transfer function? When S goes to infinity, this thing becomes 0. So I see that in this case N over D would converge to 0. And now we have completed the analysis for all parts of the Nyquist path, and now I'm ready to draw this thing. So I have real of N over D here and imaginary of N over D. So we are going to start from the point A. Point A is going to be start of this analysis. The radius is going to be infinite. The angle is going to be minus 180 degrees. I will say that it's going to be somewhere here. Okay? And then I'm going to start from minus 180 degrees, and I'm going to decrease the angle to minus 360 degrees. Okay? I'm going to turn clockwise or counterclockwise in this case. If the angle was increasing, I should turn counterclockwise. But I have a decreasing angle here. That means that I need to turn clockwise. Okay? So I will turn on an infinite radius circle here until I come to minus 360 degrees. So if I say that this is the point A, this is going to be point B. Okay? So now I will, at the end of this analysis, I need to be at the start of this table. Okay? I'm at the start of this table, and here, interestingly, this tells me that I have here the real part should be infinite and imaginary part should be infinite. But the angle should be minus 360 degrees. So 360 degrees should be on this line. Okay? But the real part has to go to infinity. What is going on here? So for a point at infinity, even if the angle is 360 degrees, it doesn't have to have 0 real part. It is something strange actually. If you look at a complex number like this, omega squared plus j omega, okay? If you let omega go to infinity here, what is going to be the angle of such a point? I know that the angle of such a complex number is arctangent omega over omega squared. Okay? If I take the limit of this thing as omega goes to infinity, what is that limit? It is 0, as you see. The angle as omega goes to infinity, the angle is going to be 0. Minus 360 degrees, I can say. But the real part is infinite, imaginary part is infinite. So we see that at infinity, strange things can happen. So this going to infinity is not really a contradiction here. Okay? That point is at infinity, it has angle 0, but it has real part and imaginary part, both infinite. Okay? So here we are at this point, and we're going to be at the start of this point in this table. Then I need to go for I now started to draw the frequency response of the system as a Nyquist plot. So I need to be remaining in the quadrant where both the real parts and the imaginary parts are positive. Okay? So I need to remain in this quadrant where both the real part and the imaginary parts are positive. Then I need to go to this point, this omega is equal to square root 2 point here. Okay? And at that point I know what the value of the Nyquist plot should be. It should be completely imaginary and it should be at j square root 2 over 4. Okay, so I'm going to go from this point to there. How you go really is not important as long as you remain in this quadrant. Because at the end here, we're going to be concentrating on the number of encirclements of some real real axis points. Okay, and that actually means that it is really not important how you go there as long as you remain in this quadrant. And then I'm going to cross the quadrants. I will go to the quadrant where real part is negative and imaginary part is positive. So I'm going to enter into this quadrant, and everything should converge to 0. Okay? So everything is going to converge to 0, but while converging to 0, I need to keep the angle at minus 180. How should I converge to 0? From here? From here? Yes. That is what I have to do here. So that is how we converge to 0. Okay? So I can actually say that this is my point C actually. Okay? This is half of the Nyquist plot. Maybe I can draw it a little bit emphasized here. So it's going to be something like this. So now I'm going to complete the other half. We are considering here real coefficient polynomials, meaning that the other half is going to be just the complete conjugate symmetry of this part. So I'm continuing to draw the plot here. So I will draw something like this, and I will complete this to the full scale. So now this is our Nyquist plot, and what I would like to do is to make a stability analysis based on that plot. How many intervals should I consider on the real axis? I'm going to look at the number of encirclements of minus 1 over k. The number of encirclements of this point, clockwise encirclements of this point, is going to be my number capital N. Okay, that is going to be the capital N, and we have also a number P. This is the number of open loop poles, or number of unstable open loop poles in open right half plane. Okay, this is the number of open loop poles in the right half plane, or the number of open loop poles which are encircled by this Nyquist path. What is this number for this example? It is just 1. This 2 is encircled clockwise. That actually means that P is going to be 1 for this example. So we have the expression n is equal to z minus p, which is the Cauchy principle of argument. Okay? And that actually means that z is going to be n plus p, and p is 1 here. Okay? So I have n plus 1 here. And this z is what we are trying to find. It is the number of unstable closed loop poles. If this number is 0, then the closed loop system is stable. This number is larger than 0, the closed loop system is unstable. So now let us try to consider some minus 1 over k's. I will start can I start minus 1 over k from here? Why? This is already at infinity. There's no there. Okay? There is no such point. These circles are already at infinity. I cannot really consider it's beyond infinity. Okay? So I need to start from somewhere here. Okay? If minus 1 over k is between minus infinity and 0, then this means that k is between 0 and infinity. Okay? This is for positive case. For positive case, how many times such a point is encircled in clockwise direction? how many times such a point is encircled by this Nyquist plot. I'm just looking at such a radial line here. It is crossed in that direction once, okay, which is the clockwise direction. So in this case, n is equal to 1. So I have z is equal to n, which is 1 plus 1, which is p. Then this is going to be equal to 2. So we see that we have two unstable closed loop poles, meaning that the closed loop system is unstable. Okay. Then I'm going to look at this interval. Okay. Again, here there is nothing here. There is only this interval, and that interval is going to be when minus 1 over k is between 0 and infinity. If I look at k here, this is the values when k is between minus infinity and 0. And in this case, how many times is such a point encircled? I'm again drawing a radial line like this, okay? And how many clockwise encirclements do you see there? There is one counterclockwise encirclement like this. It gives me -1 encirclements, clockwise encirclements, and there is one encirclement like this. It gives me +1 encirclement. Okay, so the total number of encirclements is 0. So in this case, as you see, n is equal to 0, meaning that z is equal to, I have here n is 0, p is 1, meaning that I have one closed loop, one unstable closed loop pole here. This means that closed loop system is unstable for negative k values as well. So for all k values, the closed loop system is unstable. So here, if I look at this example in terms of root locus, then I can actually draw something like this. I have real S, imaginary S here. There is a 0 at -1, and there is a closed loop pole at +2 here. And I have double open loop poles at the origin. Okay? So in this case, if I complete this root locus, I will first draw the real axis part. So we see that this interval is filled, and this interval is filled, and nothing else is filled. So now I will draw some arrows going away from the open loop poles and going towards the open loop zeros. Okay? And now I have to find, how many asymptotes do I expect? 2 asymptotes I'm expecting. They will have 90 and -90 degree angles. And if I look at the intersection points of the asymptotes, centroid is going to be summation of the closed loop, summation of the open loop poles. What is that number? This is at 2, and this is at -1. Summation of the open loop poles is 2 minus 3 diyen bizden bir adım önde, o yüzden şu 3 diyor. -1 divided by what? I need to divide by what?
3 minus 1.
Yes, 3 minus 1, which is going to be 2. So here we see that the intersection point is 3 over 2. Okay? So the intersection points of the asymptotes are here. The angles will be 90 and -90 degrees. So we see that in the Nyquist plot, we will have a breakaway point here where these poles are going to diverge away to infinity there, and one of the poles is going to go in that direction, the other pole is going to go in that direction, and these are going to meet, and I will have here some breakaway point and divergence to infinity. So in this case, by looking at that Nyquist plot, what can you say for positive k values? How many closed loop poles are in the right half plane? For positive k, the root locus is drawn for positive k values. Okay, how many closed loop poles are in the right half plane? there are always two closed loop poles in the right half plane. That is what this number is here. Okay, for positive k values, closed loop system is unstable. Again, here I can look at the complementary root locus, and in that case I have here again this similar scenario. In this case, so here whatever is in this rectangle is not included in 302. Okay, so here I will fill in the real axis, which is going to be filled. In this case, because k is actually negative, the real parts are changing. Okay, real parts will be the complement of this in this case, and this part is included, and this part is included, and I will have something like this in this case. And the asymptotes will be in that direction and in that direction. Asymptote angles would also change for negative k values. This is the case when k is negative. Okay. And when you look at this root locus, this is called complementary root locus. It is drawn for negative k values, which is not included in 302. Okay? But for negative k values, this is what is going to happen. How many closed loop poles are there for negative k values in the right half plane? 1. So that is what we are finding. Okay, that number is this. We see that for negative k values, we have instability as well. Any questions? Yes?
Now, for the open loop transfer function, the relative degree of the denominator, s squared, that determines the turn from A to B or from the angle of convergence or both?
It determines the angle of convergence to 0. Okay? So here, for example, if you have s squared and s to the 5 here, with which angle you will converge to 0 as s goes to infinity? Minus 270. You need to converge to 0 from the top. Okay? So the relative degree determines the convergence angle to 0. And actually, when you try to draw the Bode plot for the same thing, in that case, you will see that Bode plot is nothing but plotting the same thing, not in polar axis like this, but plotting the magnitude and the phase in different plots. Okay? So we take this part of the plot and we just convert it into a magnitude plot and the phase plot. Okay? So if I look at the phase plot, in that case, we might actually see that we are going to converge to 0 from minus 180 degree angle. Okay, that is what we would see in the Bode plot, and that is actually why we are including it in our analysis, Nyquist analysis. In order to be able to combine these ideas, you have to see the connection between them. Yes.
How can we stabilize this transfer function?
In general, as you see, by using a single k, we are not able to stabilize it. Okay, but it might be actually something to use. For example, so if I put a PD controller here, okay, oldu bitti. Yani buraya bir tane zero koyduk, tamam mı? Burası da doldu. Bu böyle buraya geldi. O zaman bu asimptot sayısı biraz azaldı bu arada. Artık böyle asimptotlarımız yok. Bu arkadaşlar artık birleştikten sonra buraya gidecekler. Okay. PD controller. Yeah.
We draw the Nyquist plot by excluding the other pole. I mean, radius is 2 plus in that. It would be probably harder, but
yes. Yes, you can actually do this. So here, in that case, what is going to change when you turn from the other part? In that case, P is going to change. What is going to be the new P? It is going to be 3 in that case. Okay. So, and which parts of the Nyquist plot will be modified? These parts would all be remaining the same. Okay. The parts at infinity are going to change. Okay. And I will see that in order to be able to get a similar result, this n, when p is 3, n should be -1 in that case. Meaning that if you draw the Nyquist plot for when you exclude the when you turn from this part, in that case you would get the number of encirclements -1, meaning that -1 over k is going to be encircled in counterclockwise direction now once. Okay, this is going to be -1. This is going to be 3. You would again get 2 in that case. Okay, and in this case, what is going to be the number of encirclements? If you turn from the other side, and if you draw the Nyquist plot, what is going to be this encirclement in this case? It's going to be -2. Okay, because this is 3 and this is -2. You will get again the same thing, which is going to be 1. So that actually means that point, a single point here, is going to be encircled twice in counterclockwise direction. Okay. Try to do it. Maybe it's going to be an interesting Nyquist.
My question was the radius is 2+, not the other direction. Excluding all the poles, not including all the poles.
Okay. So here 2+ dediğiniz ne?
Hocam radius'u yani 2'den fazla olan şekilde bir merkezden bir dönüş yapıyorum.
Şöyle mi yapıyorsunuz?
Ya yine infinite kalıyor. İçeride ikiniz
Ha,
sağman gibi bir durum var.
Tamam. Yani şöyle bir şey yapıyor gibisiniz sanki.
Tam öyle değil ama.
Beğendiremedim. Şöyle, o zaman şuradaki şeyleri kaçırırsınız. Bozuk polları kaçırırsınız.
Hayır, Nyquist'in infinite kısmı infinite kalıyor yine. Yani daire şeklinde.
Şöyle mi yapacaksınız? Ama şöyle, şuradan şöyle dönmeye mi çalışıyorsunuz? Şöyle mi?
Sıfır almadık ya.
Ya A'dan B'ye giderken hani 0 almıyoruz ya.
Evet.
Ben A'dan B'ye giden 2 de alıyorum. Yani biraz daha geniş tutalım o.
Tamam anladım. Şimdi anladım. Okey, tamam. Ben de jeton biraz geç çıkıyor. Kusura bakmayın. Şöyle mi yapacaksınız?
Daire şeklinde. Pencerede.
O da daire olacak. Burada garip şeyler çizmeye başladım. Yani şöyle mi yapıyorsunuz artık? Şöyle bir şey.
Evet.
O zaman buralardaki şeyleri saymayacaksınız. Ne yapacağız? Yani closed loop pole'lar burada olduğu zaman, yani şu aralıkta bir closed loop pole var. Tamam mı? O zaman bu closed loop'u saymıyor olacaksınız. O zaman yanlış sonuçlara gidebilirsiniz. Yani şuraları falan şey yaptığınız zaman basbayağı sağ taraftaki pole'ları saymamaya başlıyorsunuz. O da problem yaratacak. Anything else? Okay, so now there are 2 things remaining in this course. The first thing is going to be the Bode plots. We will do a similar thing that we did in the Nyquist plot. We will just draw the magnitude and the phase separately, and we will see the concept of Bode plot. And then by using the Bode plot, we will learn how to design a controller. The advantage of this type of methodology is the following. You can obtain a frequency response of a system, an open loop system, quite easily by making experiments on the system. Okay? If you have a system which is a black box, you don't know much about it, but if you can apply some inputs to it, sinusoids, and then if you measure the phase shift and the amplitude change, if you measure those quantities, you can always try to draw a Bode plot for your system. Even if you don't know anything about its transfer function, you can draw the Bode plot. Okay? So suppose that you are given a black box and you don't know the transfer function, then I can apply some sinusoids at different frequency to that system. And then I can look at the outputs. In the outputs, I will see an amplitude. If it is a linear time invariant system, I will see some amplitude change and the phase change. If I mark them on a Bode plot as some points, as the magnitude and the phase of the system, then I can always obtain a rough Bode plot from an open loop system. And based on that Bode plot, I can try to design a controller and I can try to understand what is going to be the performance of the closed loop system. Okay? So here, the advantage of the Nyquist and the Bode plot type of methodologies are that you can always draw these plots by making experiments on the system without knowing the transfer function of the open loop system. So the concept that is going to take us to the concept of Bode plots is going to be the concept of relative stability. We are first going to learn some performance measures in terms of the frequency domain quantities. So these performance measures will be something that you might have seen before. They are going to be called gain margin and the phase margin of a system. So these are going to be the performance measures of the system or controllers that we are going to design using frequency domain quantities or the Bode plots. So suppose that I have two stable systems. Okay? I have two stable systems with the following pole locations. I have for the second system I have these pole locations, and for the first system I have these closed loop pole locations. Which system do you think is more stable? Both of the systems are stable, but one of them is more stable. Which one is more stable? The left one is more stable. Why is that? Because it has its closed loop poles further away from the imaginary axis. Okay? We would like to do a similar thing in frequency domain. Okay? By seeing the poles of the system, I can decide how stable a closed loop system is. We will be able to do a similar thing, but now in frequency domain. Okay? And in frequency domain, we are going to be able to measure how stable a closed loop system would be. Okay? And the measures of that are going to be the gain margin and the phase margin, which we will be able to read quite easily given the Bode plot of the open loop system, which is going to be in the second hour. Let us go break.
Çizerken
O etraftan döneceğiz.
ama şey biraz farklı oluyor. Bu sefer A'dan ucundan oraya gideceğim. Sonra döneceğim.
Evet, aynen öyle. Çok daha karışık.